All right, so in today's lecture, we have the Boolean Algebra content that we are going to try to finish. We are going to start with a discussion on combinational circuit synthesis. Essentially, we are going to look into Karnaugh maps. And I'll also talk a little bit about the exam 1 that's coming up next week. So we are the date today is Feb 19th. The daily quiz for today is quiz number 8. So please go to Gradescope, take a couple of minutes to answer that. The homework that is due, that's coming up, homework 4, it's due Tuesday, Feb 23rd. The next homework, homework 5, will be posted early next week or even over the weekend. I can post that. And as usual, you will have at least a week to work on homework 5. As far as studios are concerned, Studio 1 was due last Wednesday, and Studio 2, which is your first group studio, first team studio, is due Feb 24th. So that's Wednesday of next week. For Studio 2, you need a group TA checkoff, and a studio report is also due on Gradescope. Many of you have turned it in. For those of you who haven't, please work on that before Feb 24th deadline. Next studio, Studio 3, has been posted on Piazza. I have posted quite a few resources regarding Studio 3 under the Studio Resources section. And Studio 3 is going to be a little bit different and a little bit complicated than the first two studios that you saw. So I highly recommend that you watch that video information link about Studio 3 first, and then you get started on reading the document and working on Studio 3. If you guys need partners and you're still looking for them, please post a message on WebEx Teams in your section space so that people who are also looking can come and join you. And if you still if you need my help or the TA's help, please feel free to reach out to us, and I can reach out to the students on your behalf. But the easiest way to get this done is just to post in your section space on WebEx Teams. Okay, so all of that is the announcements. Now let's talk about the exam that is coming up. So for the exam, if you go on Piazza, under the resources section, if you take a look, right at the top of the resources section, I have made an exam 1 section, right? So that is, exam is on Feb 26th. So that's a Friday. So 1 week from today. So we are going to have the exam on Gradescope, and lots of logistical details about that. I'm going to be updating this exam 1 section on Piazza with the content that is going to be on the exam, the logistics involved, from when to when is the exam going to be open on Gradescope, the practice exam I've already uploaded for you guys to work on. So Spring 2019 version is what I made. That's my exam, and you guys can start with the Spring 19 version, and then Fall 2016 version is a little bit simpler, but you can also take a look at that. I will be posting solutions to these back exams in the same space, in the same resources section over the weekend. So it'll give you some time to attempt it without looking at the solution. Let's see. There's another question in the chat box. Do we need a partner, or is it all right if we work on the studios ourselves? You absolutely are welcome to work on the studios yourself. Can we go over the canonical forms real quick? No, we can go over them, and we are going to do that a little bit slowly. Like last time, we didn't really do justice to the canonical forms. So I'll spend some time talking about that today. All right, so just to summarize things about exam 1, it's coming up. The date is Feb 26th. That's a Friday. That's 1 week from today. Please keep an eye on the section resources, under the resources tab on Piazza, to take a look at what are going to be the topics for exam 1, what are the solutions to the back exam, the logistical details, from when to when is it going to be open. So I'll be posting many of those documents on exam 1, in that section on Piazza, so keep an eye out on that. And of course on Tuesday, which is our next class, I will point that out again. Okay, let's go back to this. When are we getting the logistics for our first exam? So over the weekend. So for those of you who took Intro to ECSE, know what things look like with an online exam on Gradescope. But it is not going to be open for the duration of 24 hours. It's going to most likely be available for 12 hours. And the exam, you will have about 2.5 hours to complete it from start to finish. All the details I'll write up in a document, and I'll post that for you to read through. Okay, any other questions? Could we get access to the fall 2020 back exam too? I believe the one is closer to an online example. Yeah, I can post that as well. Sure. No problem. What else? And again, the one thing that I essentially a disclaimer about back exams is this, right? So some things are going to be similar, some things are going to be new. So when you look at back exams, treat them as practice. Don't treat them as this is what the exam is going to look like even for us. Yes, it is going to be open book, open notes. It is not going to be proctored using webcam or microphone, but it is going to be timed. All right, all those details I'll post on Piazza, you guys. All right, let me go ahead now. I think we have spent quite a bit of time on that. Let's take a look at some standard representations of logic functions. So when you represent logic functions using, say, an expression, you can do that using several ways. Like I said, logic expressions are not unique, right? So you could have several ways to represent a logic function using an expression, but that is not going to be a unique form of representation. So let's try to define these first. What is a product term? What is sum of products expression? What is a sum term? And what is a POS expression? And so on. So let's start with a product term. What is that? Well, a product term is simply an AND function between many input variables, right? So for example, I can just say, I'm just going to write the examples for product term because it's going to be very straightforward. Say for example, you have X and Y complement, right? That's a product term. It's an AND operation between X and Y complement. So that's a product term. You can also see it as X and Y and Z. Here complement, there complement. That's another product term. Or you could have different variables, A and B. That's a product term. And in fact, even if you just look at one, right, even if you had just one term X, that would be considered as a product term because it is getting ANDed with one, right? That's the equivalent of that. So an AND operation between variables. Those variables could be in their true form or they could be in their complemented form. All right, so that's a product term. Now, what about sum of products expression, which is essentially your SOP expression, sum of products expression? Well, over there, you are taking a bunch of product terms and then you are summing them, which means we are ORing them, right? So, for example, you could have X and Y complement or X and x complement or y or z complement. That's a sum of products expression. Is it the simplest SOP? Maybe, maybe not. I don't know yet. I did not attempt to simplify it. But I know that this guy is a product, this guy is a product, and I am ORing them. Not this is ORed. Right? Summed. Not the arithmetic sum, the logical sum, which is the logical OR. So you take a bunch of product terms and you put a OR gate between them and you get a sum of products expression. Again, let us talk about this. Is a sum of products expression a unique expression for a logic function? So when I say f equals this, is this the only SOP form I can have for a logic expression? No, right? Absolutely right. Sum of product expressions are not unique. All right, now let's go to the other side of the coin, which is a sum term. So when you're looking at sum term, earlier we were putting an AND gate between the input variables. Now we are going to be putting an OR gate between the variables. And those variables, input variables, could be in their true form or complemented form. So for example, x or y complement, right? That's an example. Or you could have x or y complement or z complement. That's another example. And if you look at just A or B, right, it is the same thing as saying A or 0. So even that is, so when you have just one variable, it kind of doesn't fall under the category of sum. It actually falls under the category of both a sum term and a product term. Because you put an OR gate with a 0, you get back your A. So that's your sum term. Now, using a bunch of sum terms, you can put an AND gate between them to get a product of sum expression, which is your POS. Now, just a quick pointer here. On the exam, you will, and on the homework, you will see me talk about SOP and POS, and in fact, canonical SOP and canonical POS. Because these terms look very similar, sometimes, a lot of times, students, see SOP, but they think it is POS. And actually, the other way happens a lot more. So make sure you pay attention to the terminology, right? CSoP versus CPoS. They're very different things. All right, so POS, right? What is POS? Well, I need to do a product of all those sum terms. So for example, I can have another function here, logic function here, which I'm calling G, and I can say this is x or y complement ANDed with something else, x or y complement or z complement, right? And I could have also added x here, right? So that shows you that this is a product of sum expression in which you are doing ANDed, right? All the sum terms are getting ANDed. So that's your POS expression. Again, just as the SOP, a POS expression is also not unique. Now, before I define the normal term, let me actually define the min terms and max terms first. Because once I do that, then it'll be easier to kind of talk about a normal term. So let's do min term first. So for min term, let's say I use red, sure. So min term is a product term. It's a product term in which suppose you have n variables that are involved in the function. All n variables are represented either in true form or complement form, either in true form or complemented form. So for CSoP, all terms are min terms. You got it. that's exactly how we are going to define it. We are going to say canonical sum of products expression is a sum of minterms. That's it. All right, so it's a product term in which all n variables are represented, which also means that I need to know what are all the variables that are involved in my logic function, but they should be represented in true form or complemented form. For example, let me do the example in black. I have f, a function that has variables x, comma y, comma z. The function, logic function f, depends on input variables x, y, and z. And I'm saying that that function is x and y, or x complement and y and z complement, right? So the question now is, am I having minterms in this expression, or am I missing something here? Now, if you notice this second term, one is a minterm. Yes, only this guy is a minterm because it has all x, y, and z. Those are your n variables. In this case, 3 variables. Those are represented in either their true form or their complemented form. But this first product term is actually not a minterm. So this example is not going to work unless I add this with a z, for example. I could have done z complement as well, but now x, y, and z appear in each product term that are being summed up. So now I have minterms, right? Where are my minterms? This guy is a minterm and this guy is a minterm, right? Consequently, I can call this a canonical sum of products expression. So short form CSoP. And you can define this as sum of minterms. So in minterms, you are trying to AND them together, essentially trying to see whether your logic function can become 1 or not, right? Like when you are ANDing them together, your unique entry in the AND logic function is what? When both variables are true, then your output is true. Why is it called a minterm? I don't know. There is a minterm and there is a maxterm. You're trying. I specifically don't know why that min is there. I can try to look it up, but I can tell you that it is trying to make that particular product term go to a 1, a true. Next, max terms, the story is going to be exactly the opposite. For example, I can actually copy this and paste it right here, but maybe I need to kind of do that, right? So for max term, what is it going to be? Again, n variables is what we are considering. In this case, it's not going to be a product sum, a product term. It is going to be a sum term. Sum term in which all n variables are represented either in true form or complemented form looks good. Next, for the example, I'm going to have the function have max terms in it, right? So for example, I can have a max term here as x or y or z, and I can AND it with x or y complement or z complement. Now, as you can see, f was dependent on x, y, and z. Both x, y, and z, all 3 of them, right, are represented in both these sum terms. So this would be max term number 1, max term number 2. Let me separate that a little bit. And those are your max terms. And the function itself, I'm going to call it a CPoS, Canonical Products of Sum expression, which is CPoS, is a product of max terms. And in this case, we are doing this or this or this. So essentially, we are trying to see whether the inputs make it into a low or not. Are we also trying to make a 1 for max terms? No, you're trying to make it into a 0, right? Because if you look at the OR truth table, it's connected to K-maps. I see. All right, I'm going to have to think about that a little bit. But if you look it up, if you find the answer, let me know. All right, so what do you have here? All right, so X or Y or Z, right? So you're trying to look at the unique entry in the OR table. So if you look at the OR truth table, what do you see? You say, if any one of the input variables is a 1, your output goes to 1. But the unique entry is both inputs are 0 and you get an output of 0, right? So you're manipulating that expression to look at that 0 or 0 equals 0 case. But for AND, you were looking at 1 and 1 equals 1. That was the unique entry for the AND situation. Okay, so I think we have covered all of them except for normal term, right? Normal term is essentially not a minterm or a max term. It would be called a normal term. Neither a minterm or max term is called a normal term. So if you have things like X and Y that we had earlier, that would be a normal term. X or Y here, that would be a normal term. So it doesn't have to obey any rules as far as all the variables being represented is concerned. All right, so we talked about these. All right, questions about the representations, the standard representations. Essentially, I'm looking at understanding of CPoS, SOP, POS, CPoS, and CSoP. Now, let me ask you guys a question. Is a canonical canonical sum of product expression, CSoP expression, is that unique for a logic function? Yes. You got it. Yes. So CSoP expressions are unique because they are directly tied to the truth table, which is also unique for a logic function, right? And similarly, even the canonical products of some expression would be unique because again, it is tied to zeros in the truth table. And truth table we know is a unique representation of a logic function. So CSoP, unique for a logic function. CPoS, also unique for a logic function. Okay. Now let's take a look at truth table and its min terms and max terms. So we have a truth table over here in which we have 3 input variables, X, Y, and Z. Now, the function itself could have, so these are my 3 inputs. Let me just put, right, that's my inputs. And you could evaluate, say, one output, right? F. F is your function that depends on the 3 input variables, X, Y, and Z. So this is one output. Would you have more outputs in a truth table? Sure. You can have X, Y, Z as inputs, and you can have one F, one column for G, and one column for H. So you can have multiple outputs for a particular logic a particular sequence of inputs. Now, for our convenience, we have numbered each row. And the reason why we have numbered each row is because we want a compact way, simply a number, to identify our min terms or our max terms. We just want a number. Why should I write X complement and Y complement and Z complement when I can simply say this is min term number 0? Why should I say X or Y or Z when I can simply say max term number 0, right? So compact representation requires identifying each entry here with a row number. So this is your row number. So as you can see here, min terms are a product term. So f will have at most 2 raised to the number of literals. F will have at most 2 raised to the number of literals. You mean the number of rows in this? Yes, number of min terms or max terms. You are right. Yeah. So at most 8 min terms, and that would be if everything here was 1. At most 8 max terms, that would happen if everything over here was 0, right? Over here, sorry. If everything over here is 0 in the F column, that means that it has all 8 max terms. And everything over here, if it is 1, 8 ones, that would mean that the number of min terms are going to be 8. You're absolutely right. Those are at the maximum min terms or max term. Now, how are we writing this each min term here? Well, if you look closely, we defined min term as a product term. Right there it is, right? X complement and Y complement and Z complement. So there is a product going on. All 3 variables are represented, sure. So that qualifies as a min term. But why is it associated with row number 0? Well, it is because when X is 0 and Y is 0 and Z is 0, and you evaluate for those particular values of X, Y, and Z, if that goes to a 1, then you will write that as a 1 in the truth table. So that's X complement and Y complement and Z complement. And actually, if you are very comfortable with the binary code of decimal numbers, then you can say 001, 010, 011, and so on, right? So that sequence of either complementing the variables or not complementing the variables exactly follows your binary counting sequence. So whenever you have a 0, you're complementing them, and whenever you have a 1, you are not complementing them. But how are you getting these? By evaluating a given function for those 3 input values, 000 all the way down to 111. And it would be very convenient if I say wrote this particular min term as small m for min term, and I provide a subscript of 0 indicating the row number, right? So that is my min term 0, small m subscript 0. Similarly, okay, let me take a look at this. What would be this guy? X and Y complement. Oh, okay. So Andrew said M5, but the correct answer is small m5, right? So there is the difference. So the way you identify min term and max term is a small m and a capital M. So make sure that you keep them distinguishable. So small m5, right? Good. So that's your min term 5, and it's a product term. It has X, Y, and Z, and it is corresponding to row number 5. So everything is in order here. Now let's talk about max terms. For max terms, you're actually making things 0, right? Like X or Y or Z, 0 or 0 or 0. You got a 0, right? So those are an OR function. I'm going to need a slightly different character for this max term. So I'm going to use the letter capital M to identify a max term, but it is going to correspond to the same row number. So this is going to be max term 0. And you have to be a little bit careful here because, often I see students get confused with identifying these, especially the numbers, right? So if you have, X complement or Y complement or Z complement, then I've often seen people say that is max term 0, but it is not. It is what? max term 7. Good. Now, a particular function could be, why would you want to see when f is 0? Well, okay. Here is the answer to that. If I flip a coin and suppose it lands as heads, one way for me to describe what happened would be heads was on top. The other way for me to describe that same situation would be tails was not at the top, right? So any logic function in your output is going to be a bunch of zeros and ones. But if I tell you where all the ones are, then you automatically know where all the zeros are, right? Because it is this or that. So if you are, essentially this gives you an alternate way of essentially describing the logic function. Either you can look at the zeros in the truth table, or you can look at where the ones are in the truth table. But if you know where the ones are, you automatically know where the zeros are. So it's just customary we use SOP. No, there's no benefit like that. It's just, so SOP tends to be a little bit, like you said, customary, mainly because it is easier to deal with SOP. But there's no clear benefit of other than just a preference. All right, let's move on here to canonical forms, and we have already kind of talked about it. So let's just recap that. Truth tables are uniquely going to identify Boolean functions. We have said that many times. And there are two canonical forms of Boolean expressions that are derived from the truth table. One is your sum of products, and the other is your product of sum. Now, SOP, we are like I said, we are trying to represent the function ones. We are taking a look at where are the ones in the truth table. And for POS, we are looking at where are the function zeros in the truth table. So sum of product versus product of sum. Now, you know, in order to just be complete here, these are both canonical forms. So this should be canonical sum of products and canonical products of sum, right? Because we are looking at the standard canonical forms here. I think it's going to be the representation is going to be very clear once you start looking at an example. So we have a sample truth table over here. We have 3 inputs, A, B, and C. We have only one output, but we are writing that particular output F. That's your first column for F. But just to see how things work out, we are also including a column for F complement, which is exactly the opposite of F. So we only have one output variable, but just to see how things are going to play out, we are also writing the F complement column. And like I said, it will make my life very easy if I index things using a row number. So what I'm going to do is I'm essentially going to put a number here and I start at 0. I've also seen this happen many times. Does the row number start at 0 or 1? Starts at 0. 1, 2, 3, 4, 5, 6, 7. Also not 7. All right, so once I have indexed each particular entry with a row number, then I'm essentially, when I try to list things out in a compact manner, that's going to help me. So what do I have here? What should I call this particular expression? Canonical sum of products is absolutely right. It has all the minterms. I have ORed, summed all the minterms. Now, question is, how did I go from the truth table to the logic expression? Well, zoom in on this particular column. highlighted in yellow, right? I am looking at the canonical sum of products. So I'm essentially focusing on where the ones are in F. And it looks like the ones are over here, 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 and here. That's it. So now let's try to look at this guy. F is a 1 when A is 0, B is 1, and C is 1. That translates to F is 1 when A complement and B complement and C, A complement and B and C goes to a 1. So that entry right there, let me actually, use a pen here, and this maps to that. A is 0, B is 1, and C is 1. Next, this guy would map to that term. A is 1, B is 0, C is 0. And similarly, that would map to that. And this would map to that. That would map to that. So for 5 ones in my, we could also call it M327, right? Yes, that's exactly what we are going to do. Because if my truth table had 32 entries or 64 entries, I would not have the time or patience to list out, a bunch of minterms in their long form, which is, exactly why to make things compact, we need to index things. So we have got 5 ones for F, and we have got 5 minterms in the corresponding canonical sum of products expression. And now if you notice, for F complement, because F complement is the exact opposite of F, I just flipped 0 to a 1, 0 to a 1, 0 to a 1, 1 to 0, 1 to 0, 1 to 0, 1 to 0, 1 to 0. And if I was interested in writing a canonical sum of product expression for F complement, I would say F complement equals A complement and B complement and C complement, or it equals or A complement and B complement and C, or A complement, B, and C complement. And that gives you those three. Right? So let me identify those three guys in a box here and a box there. If I have one output, I'm able to write an expression for F. I'm also able to write a canonical sum of product for F complement. Now, like Andrew pointed out, it would be really helpful if I had a compact way of writing things, say for F, right? So these arrows are making things a little bit messy here. So I'm going to erase those guys. And instead, I'm just going to say this is red box and that is my red box. Now what I'll do is I'll have a separator in the middle, and I'm going to write a shorthand. How do you use shorthand to write the same thing? Well, I would say F, what does F depend on? Very important to list out the input variables, and more importantly, the sequence of those input variables. In our truth table, we were using A as our most significant variable because it was all the way to the left, and C was effectively your least significant input variable. Does it have to be that way? No. You could have moved C here, you could have moved A here, you could have moved B here. But if you change the order of the inputs, all the entries in the output columns also need to be adjusted. The function doesn't change, but the shorthand notation might change when you change the order of the inputs. So when it comes to the shorthand notation, you absolutely must explicitly write the order of the input variables. So let's do that here. A, B, and C. And I'm doing a sum, right? So one way of doing it would be, what do we have here? Minterm 3, minterm 4, 5, 6, and 7. All right. So one way of doing it would be minterm 3 plus minterm 4 plus minterm 5 plus minterm 6 plus minterm 7. That would be one way of doing it. Or I can write it using a summation sign. And I can say my inputs are in the order A, comma B, comma C, and the minterms that are involved are 3, 4, 5, 6, and 7. And similarly, I could have done that for F complement. So F complement, can you guys tell me the shorthand notation for F complement? Zero, 1, and 2. Perfect. And now you can see these two are always going to be inverses of each other, right? So if 0, 1, 2 is going there, 3, 4, 5, 6, 7 goes there. And so whatever is not here goes there in the expression for F. So if you know one, you know the other. All of this is for what? Sum of products, right? This is your canonical sum of products expression in the long form, and then all of this is canonical sum of product expression in the shorthand notation. All right, questions about this? Could we also do sum from 3 I equals mi if we had a lot of terms? You can, absolutely. But just be careful. This kind of situation doesn't happen very often. So the ones are not always in a continuous manner. So you will have 0, 1, 0, 0, 1, 1, 0, something like that. So that might not be the best way to deal with those kind of situations. Let's see. For homework 4, the last problem doesn't have the summation sign. Is it something else we will learn? So if it doesn't have the summation sign, then it should have this. If it doesn't show it up like this, it should have this. I'm not exactly, I don't exactly remember the details of that problem, but I can just tell you a couple of things here. One, you can translate a sum of product expression into a canonical sum of product expression. You can do that. All you would have to do is take that SOP expression, make a truth table for it, look at where the zeros are and the ones are, and you know it. Right. So that is a canonical product of sum. Just hold on. We'll get there. We'll get there. We could also determine canonical product of sum quickly by doing De Morgan's to F complement. Yes, you're right. All right. So you guys are pushing me to go faster. Sure, we will do that. So this particular slide essentially lists out the complete expression for the previous truth table and also in its shorthand notation, both for F and for F complement. And we have discussed this, so I don't think there is any necessity for going further with that. So now let's take a look at product of sum expressions. So these are going to be focusing on where are the max terms, right? So let's take a look. Again, we will need a row number, right? So let's just go back here and steal our row column. And we will come back here and paste our, oh, shoot. I think, but in this time I would have simply written up this guy. And to make things worse, I missed an R. Alright. So we have the same truth table, and now we have ABC as your inputs, F is your output, and F complement is also being mentioned here. So if you're looking at product of sum expression, what are you looking at? Well, if you just focus on F first, so we'll focus on F first, right? So we are looking at this particular entry in the truth table. You're looking at where are the zeros? Well, the zeros are over here and here and here. 3 zeros in the truth table. Each of those will correspond to a max term. So what is the max term for this position? That is row number 0. Well, it is A or B or C. So let me use the same way here. So these map to that. And then similarly, if you did this for F complement, where are the zeros? It's over there. 3, 4, 5, 6, 7. And that would be for F complement right there. Let me just talk about how we got this, right? If you look at the 0th row where there is a 0, if A is 0 or B is 0 or C is 0, F is 0, right? That maps to a sum term which is A or B or C. And the second 0 and the third 0. So you've got 3 sum terms that are being ANDed in that canonical product of sum expression. Yeah, canonical product of sum expression. And similarly, if you look at F complement, the zeros are in the location 3, 4, 5, 6, 7. 5 of them, those are corresponding to these 5 sum terms. So for max terms, that is pi notation, it's called product equation of sum. Yes, for max terms, yes. So you will be indexing max terms here. For example, this 0 corresponds to what? Let me highlight that in blue. This 0 corresponds to when F complement is a 0, and we are writing the thing for F complement, so that's fine. F complement is a 0 when A is 0, B is 1, and C is 1. So A should be 0, B complement should be 0, or C complement should be 0. In other words, A should be 0, B should be 1, C should be 1. And you add them 5 at a time. All right, so let's also do the shorthand notation for POS form. What would I need to do? Well, I would need to write F. I would need to explicitly write the order of the inputs. F is dependent on ABC. And instead of sum using the summation sign, I'm doing a product using the pi sign. Again, I need to explicitly mention ABC over here. Now, you might ask, why did you write things over here and why did you write things again over here? Well, this is kind of optional. This is what is more important. If you were writing this or not, if you skip this, then you absolutely must do that. Inside, I'm only going to index the max terms. So what do I have for max terms for F? Row 0, row 1, row 2. This is sort of the same thing as saying F equals, here is very important to write ABC, equals max term 0 and max term 1 and max term 2. Or short form, just the numbers. So they are all the same. Let me put a divider right in the middle, right there. Now let's go to F complement. We've got the 5 sum terms listed out. Now let us try to write it in the compact manner. F equals pi, F complement equals pi ABC. What do I have here? Row 3, 4, 5, 6, and 7. What does that pi thing mean? All right, so pi means a product. Just as summation means a sum, pi means a product. Where is my, let me say sum I equals 1 to n x sub I. What is that? That means you're trying to do x1 plus x2 plus x3 plus and so on up to xn, right? You guys are familiar with that. Pi essentially takes this and converts it into a product. If you're okay with the, no, they are very close to, and multiplication product. Does that help clarify? No, no, that must have been painful. What are you saying? All right, okay, so here, how are we doing about the pi notation now? Are we doing okay with it now? Is, think of it as the summation sign, but you're trying to multiply things out instead of add them up. All right, brilliant. Right, so you see, we did M0 and M1 and M2, right? That's why we had a product. Earlier, we were doing minterm 0 plus minterm 1 plus minterm 2. So now that was the summation. Okay. I also want you guys to notice this. Whatever was listed as a max term for f was not listed as a max term for f complement, and the other way around. In other words, if I gave you the set of max terms for f, you would be able to tell me the max terms in f complement. And now if you start noticing a pattern between this and that, so this is just the same kind of notations that we have been talking about in shorthand, sort of a repetition here, so we don't need to worry about that. Now let's talk about the conversions between canonical forms. The same functions, so it's the same truth table. We are trying to explore complementary relationships between the minterms and the max terms. So suppose you have a SOP form for f, right? Sum of products in which the minterms are 3, 4, 5, 6, and 7. So if 3, 4, 5, 6, 7 are the rows in which you have ones, then of course 0, 1, 2 are the rows in which you have 0. So those will be your max terms. Like I said, heads is the same thing as saying not tails. Right, you can look at it using De Morgan's law as well. Yes, when you're complementing things, you are converting that and to or to and you are inverting the literals as well. And we'll try to take a look at De Morgan's law and how it applies over here as we go on. And the same thing applies for f. You see, for f complement, if you had the sum of product expression for f complement and you had minterms 0, 1, and 2, then you also know the max terms as 3, 4, 5, 6, and 7. So can we get normal terms in these scenarios? No, these are all for minterms, max terms, canonical conversions. So you would encounter normal terms when you are trying to most likely simplify things out. That's when you are going to go into normal terms. But over here we are looking at, essentially taking things in a unique manner, right? Like the truth table, unique representation, canonical forms, unique representation. Now, once you use Boolean manipulation or K-maps or some other technique to reduce the expression, then you will get into your normal terms. Could you do like A complement or B complement or from the truth table and they would be normal terms? Yeah, they would be normal terms, yes. But, you would not be able to quickly get to that expression directly from the truth table, it would require you some, like, you would have to observe all right, let's see. Okay, so we were talking about a complementary relationship between minterm and max terms, but also there is a complementary relationship between f and f complement, right? So if you have the SOP function for f in the SOP form or the canonical product of sum form, then you also have that complementary relationship for f complement. So if you have SOP for f, the SOP for f complement is going to be complementary. 0, 1, 2 goes there, 3, 4, 5, 6, 7 goes there. And the same thing applies even over here. So there are two complementary relationships. One is for SOP versus POS, other words, min terms and max terms. The other complementary relationship is in the function itself, f and f complement. Now, sometimes you also have a situation where the outputs you don't care about. Those are called don't care situations. So, output has to be 0. Okay, that's well defined. Output has to be 1. That's well defined. I don't really care whether the light is on or off. For this particular input situation, I don't really care whether the light is on or off. That is what we call a don't care situation. So what should I put in the truth table if I have a don't care situation? Well, X, you're right. So let's try to take a look at some examples where incomplete functions, meaning functions with don't care situations, happen, and how do we incorporate that into our standard representations. So these inputs cannot happen in a good design, right? So in a good design, you would not leave it to chance or leave it to like something random. You would have to, in a good design, you would want them either to be off or either to be on, right? Let's try to look at an example in which we are going to take a BCD code and we are going to increment it by 1. Now, binary coded decimal, right? How many bits do you need for representing a binary coded decimal? So you have codes, decimal codes that go from 0 to 9, right? Decimal codes go from 0 to 9. So how many bits? 4 bits, right? So you would need 4 bits to identify the 10 codes, 0 through 9. Well, 4 bits can give you up to 16 possibilities. You only are going to use 10 possibilities over here. You're only using 10 possibilities over here. So what happens to the remaining 6 possibilities? You don't care. You may not care, I should say, right? You may not care. Sometimes good designers do care about that, and they might force the output to be low or high for those particular situations. So let's take a look at BCD numbers over here. This is a table in which on the left you have the number itself. Those are decimal numbers, essentially your 10 decimal symbols, 0 through 9. Each symbol is being represented by 4 bits, 0, 0, 0, 0, all the way to 1, 0, 0, 1. Those are your 10 representations for symbols 0 through 9. However, if you go further, because with 4 bits you can have input of 1, 0, 1, 0 all the way down to 1, 1, 1, 1. You don't care about that. So you would associate a value of X, which represents a don't care situation. So how do I use this kind of a scenario and be able to represent it in a truth table? Let's take a look at that with an example. So here we have an ABC. Those are my 3 input variables to this truth table. And I only have one output, which is F. And there are a couple of zeros, a couple of ones, and there are a bunch of don't care situations that are happening over here. So the question is, how do I represent this in a canonical sum of product expression for F? Let's try to do that. So what I'll do is I will say CSoP, and I'm going to list it in shorthand. F equals, I have a summation. Yes, I need a summation. Why? Because I'm doing a sum of product. What is the order of my inputs? Very important. I need to specify the order in which they appear in my, is that M1 plus M4? Right. So summation ABC, and then I'm going to have this guy is for 1 and this guy is for 4, right? So I'm going to say this is 1 here and 4 here. So that takes care of these two. So let me color code this. 1 here, 4 here. Done and done. However, I don't care about these 4 guys, which means they could be a 0, could be a 1. I also need to write them in my canonical sum of product expression as this. Don't care. What are the minterms that you are not caring about? 2, 3, 5, and 7. Yes, absolutely right. Let's color code that in blue. Now let's do canonical product of sum for the same F. I'm going to have a pi. I'm going to have the sequence of inputs A, B, and C, and then I'm going to have. Why do we need that? What do you mean? Why do we need this? Yeah, because when I say don't care, it may be a 1, it may be a 0. I don't know that until I actually implement it, right? When you have a particular truth table, you need to eventually put it into a hardware form. You actually have to implement it. But once it is implemented, it will no longer be a don't care. It will either be a 1 or a 0 after it is actually implemented. So I still need to provide that into a logic form representing that, okay, those are don't care situations. So depending on how you actually put it into hardware form, there might be a 0, might be a 1. All right. So let's take a look at pi. What do I have for pi? I have, what should I write here? Maybe a 0 for the first 0 and then 6. Right? Color code it. Then what do I have? The same thing. It could be a 0, it could be a 1. So it should fall in both categories. You guys see that? So you have got canonical sum of product, in which you know how to deal with at least representing a don't care even in the canonical product of sum. All right, questions about this example? Do we still need to add don't care terms for CPoS? Yes, you absolutely should. No, so that's a very good question. So you might think that because you are ANDing them, you have to AND them, but no, the representation is pi of all the max terms or don't care of all these terms. So it's plus you would need. All right, other questions, guys? So don't care situation where right. I don't know. All right, you guys, questions about this? If not, then we need to start talking about something that excites everyone in CoCo, which is K-maps.